Good evening, everyone. Welcome to our video sessions for Unit 1.5 of Algebra 2. So, why is this Unit 1.5? Well, we're going to be reviewing some of the things that we need from Algebra 1, and we felt that it is so important for us to remember and review some of the concepts from quadratics that you did at the end of Algebra 1 that we tried to make this its own little standalone unit. We're going to use this concepts for the rest of the class going forward for many of the units. So it's important for us to have our freshest mind available for all of these units. So let's get started, shall we? The things that we're going to be doing, even right away from the beginning, you might remember some from Algebra 1, but even if not, that's okay. That's why we're here. But they are going to be applicable to a lot of things going forward. So we have to understand the basics, and so that later on, we're not reinventing the wheel for our future units. We can say, hey, this is just like what we did with quadratics, just one step further. That's the plans, but we need to have a really good foundation for that. So with that in mind, let's get started. All right. So let's do a little warm up here. Okay? So we have a diagram. So reviewing our materials from sequences, let's take a look what's happening here. We have, looks like a growing pattern of some kind. It's always useful to start by counting boxes, right? So how many boxes are in, oops, oh, that's not what I wanted. There we go. There we go. Perfect. How many boxes are in each step? Looks like this one has 5. Yeah, this one has 9. And this one has 13 boxes. Excellent. So we have 5, we have 9, we have 13. But more importantly, look at the shape that's happening here. It looks like we have a single box with 4 corners. We have a 2 by 2 with 4 corners, and a 3 by 3 with 4 corners. So what do you think would happen if we kept going? Looks like we're going to get maybe a 4 by 4 with 4 corners, like this. That might be step 4. And then the next one looks like it's going to be a 5 by 5, an even bigger one. 2, 3, 4. 1, 2, 3, 4. And we're going to have 5 corners here. 4 corners here as well. All right. So we can do that. Now, how many small squares are in each of these steps, right? So let's write out the pattern. We had 5, 9, 13. What's the next one? Looks like it's 4 times 4 and 4, so that's 20. And then the next one is 29. Okay. So, is this arithmetic or geometric? Trick question. Neither. Because it's a different number being added each time. Here you're adding 4, then you're adding, looks like 4 again. So 5 to 9. Wow, that's not 9, that's 8. Oh, goodness. That's 8. Okay. So, whoopsie, first mistake. So that's 8. So 5 plus 3 is 8. So plus 3, plus 5, plus 7, plus 9. The next one would be plus 11. But that also means it's not geometric either, because 8 divided by 5, 13 divided by 8, 20 divided by 13, those are all different values. So this is a neither sequence, which means maybe we can write it as an equation. So we're going to write an nth term equation. So how would we do that? Well, let's see. In each case, it's especially evident when you get to the bigger diagrams. You have a square with 4 corners added on. So 5 times 5 plus 4. 4 times 4 plus 4. So what would that look like? F of n equals, we're going to take the step number and multiply it by itself and we're going to add 4 to represent those 4 corners. Now, what is n times n? N times n is n squared. So my equation becomes n squared plus 4. Now, how many squares would be in step 18? So f of 18 is equal to 18 squared plus 4, which is 324 plus 4, or 328. So 328 squares would be in that one, and we can do that directly because it's an nth term equation. But you might remember that equations that have an n squared term in that are a very special kind, and those are called quadratics. A quadratic is any equation like this one here, where the biggest power is an n squared, something that's been squared. So a quadratic expression in a more mathematical definition is an expression x that is equivalent to one of the form ax squared plus bx plus c, where a, b, and c are constants and a is not 0. So why can't a be 0? So if a is 0, what happens? 0 times x squared goes away, and you're left with bx plus c, which would be linear. And, well, we don't want that, right? We don't want linear. So we're going to hopefully not let that happen. Okay. But if we look at these equations, this table, these different red graphs here, and all of these examples, these are all considered quadratics because no matter who they are, what they look like, we can convert them into an equation of this form. Now, it may not be evident what the equation for this one is. I'm trying to look at it and see if I can come up with an equation, and I'm not really seeing it right away. Actually, I think it is, now that I'm looking at it, it appears to be 2x squared minus 6. But, knowing what the equation is from this table, we'll get to that part later. But these, I could, with some work, knowing the scale, I could find an equation for each one of these as well. And then over here, all of these are also quadratics because notice how they have this x squared term. And they don't have a higher power. If it has a higher power, like an x to the third, that's completely different. Even if it has an x squared term. But we'll get more to that in a future unit. What's interesting, though, is when you get to ones like this one. How is this equation a quadratic when it doesn't have the x squared term? Well, the reason why this one is considered a quadratic is because it has two x's, and notice here, boop, there's a multiply. So if I wanted to multiply this out, I would multiply x times x, and that's where it gives me the x squared. And so we'll look at that a little bit later today. So some equations are written in separated form like this rather than the x squared. And that's why in the definition it says equivalent to an expression of the form. That means there's many ways to write a quadratic, and each one will have its own special characteristics that are useful to know. Okay, here are some of the parts of the quadratic. A vertex is always going to be the point that is considered either the highest or lowest point of the parabola, depending on which way it's facing. The vertex is, another way to look at it is it's the point where the graph changes direction. And it's also where the line of symmetry crosses the parabola. So parabolas are symmetric. No matter which way they go, whether they face this way or whether they face this way, it doesn't matter. The parabola is symmetric, and the point where the symmetry crosses the parabola is called the vertex. Now, the other important pieces of the graph are the x and y intercepts. Now, unlike other equations, x-intercepts are a little kind of interesting here because you can have, as you see in this graph, you can have multiple x-intercepts. Now, the lovely part about the y-intercept is that there's only one. You will only ever have one y-intercept. So let's get some room here. So you'll have one y-intercept, and you will always have that y-intercept. Sometimes it's 0, but it will always exist. But for x-intercepts, you could have either 0, 1, or 2 x-intercepts, depending on where the graph is on the axis. So here's a case where you have 2. If your parabola did more like this, then you'd have a single x-intercept, and that would be the vertex. That only happens when the vertex touches the axis, because it'll come down and bounce off. The other situation that occurs is when your parabola is just completely facing away from the axis. And in this case, you won't have any x-intercepts. And algebraically, you can actually see when this is going to happen. And so we're going to do that as we go through this unit. Here's another word that you're going to see a lot, the word 0. A 0 of a function is an input that leads an output of 0. So, for example, if I were to plug a number in for a function, and when I do the math, it gives me an answer of 0, then A is considered a 0 of f. Not that it's equal to 0, but it's a 0. Here's the thing. For our work on parabolas, a 0 is equal to an x-intercept. Now, can you see why looking at this graph? It's because the x-intercept, like this point here, is 3, 0. So this is telling me that if I plug 3 into this function, that I'm going to get 0 for an answer. Same thing here. If I plug in -1 in for the function, I'll get an answer of 0. So a 0 is another word for an x-intercept. Sometimes you'll even also hear the word solutions. And the word solutions for this unit will also refer to the same concept. So you may wonder why we need 3 different words to refer to the same thing. Well, this is just kind of how math develops. Short answer is math develops in lots of languages. And depending on the languages of the user and the specific terminology that they're used to, they might call it different things. Also, x-intercept, is basically references the graph, right? And it implies that we're looking at the graph. 0, where solutions, implies that we're looking more at the algebra, like solving to find the answer that gives a 0. So just keep in mind that you will see all of these, and they will all be interchangeable. Okay, next. All right, so let's take a look at this one. So here's our first kind of introduction to parabolas. Here's a graph, and it's defined by this function. All right. So my first question here is given this line, and we have no numbers on it. But one of the powers of parabolas is based on some simple information, we can easily find what all these points are. So let's start with the equation, x plus 1.6 and x minus 2. This is a special kind of quadratic graph called factored form. When an equation is in factored form, you have the two x's that are split. And I can multiply them together to get the x squared. Notice here that it's two factors multiplied together. And that's going to be key. So you can recognize factored form when it has two separate x's as two separate factors being multiplied together. Sometimes they're not both in parentheses, but at least one should be. Anyway, let's look at the questions. Now, which points represent the zeros of the function graph? Well, based on our last work that we did, it looks like the zeros are the same as the x-intercepts, right? X-intercepts. And so it must be these points here, AB and CD. And how do we know that? We know that the zero is these points give an output of 0, and that's what a 0 is. All right, so which point represents the vertical intercept of the graph? Well, okay, vertical, so vertical line, intercept, clearly it's got to be that point. So this must be the point E comma F. And how do we know that? Crosses y-axis. Okay, now, using the graph to the right, can we identify all the values of A, B, C, D, E, and F? Ooh, okay. So let's go through one at a time. So we have A, B, C, D, E, and F. Okay, so let's start with the easy ones. Now we know that these zeros give an output of 0, right? So which part of the coordinate is going to have an output of 0? So the output is always the y-coordinate, right? Which is always the second number in the ordered pair. So B and D must both be 0 because these points have to be something, comma 0. And then here, this one also be something, comma 0. What about this point? Because it's on the y-axis, now what was happening is the input, or the value of x, is going to be 0. So now we know that E is also equal to 0 as well. But how do we figure out these points? Well, here's the thing. What we need to know is what values here I'm going to plug into this equation to give me an answer of 0. Well, how would I know that, right? But let's think about it. I need this equation to equal 0. Well, what I know is that it's a product right here, right? Boop. This is a multiply of two terms. So if I want to multiply two things together to get 0, what must happen? So it turns out that one of these factors has to be equal to 0. If A times B equals 0, then, or actually let's not use A and B because we're already using that in this problem. So let's just use two other things, okay? So let's use R times S. If R times S equals 0, then R equals 0 or S equals 0. The only way for this to equal 0 is that either the first factor equals 0 or the second factor equals 0. So how can that happen? Well, what number can I plug in for x that makes this equal to 0? Well, what plus 1.6 equals 0? So if I could do that, what I could do is, on the aside, I could solve an equation. X plus 1.6 equals 0. Well, I would subtract 1.6 from both sides. Hey, well, that just means it's negative 1.6. Now, what about this one? If x minus 2 equals 0, then x must be 2, right? So x is equal to 2. Now, which one of these points is most likely to be the negative 1.6, and which one of these is equal to 2? Looks like this one's the negative one. It's on this side of the axis. So A is going to be the negative 1.6. And then C has to be equal to 2. All right. Now what about F? So to find the y-intercept, we have to take the 0 and we plug it in for x. And so to find that, I simply do 0 plus 1.6 and 0 minus 2. Well, the 0 doesn't change much, right? You don't even really have to write that. It becomes basically 1.6 times negative 2. So to find the y-intercept, factored form is nice and easy to do it. You just take the two you take the two factors in the expression and you multiply them together. It also, in this case, you could multiply the x-intercepts together, but that doesn't always work. It does work to multiply these two together. So 1.6 times negative 2 is negative 3.2. And that's going to be the y-intercept. So these two values of a and c, these are called the x-intercepts or the zeros. Both terms work. So keep in mind how I got these by taking the factored form and just changing its sign. That's really all that has to happen for that here. But there's a few different cases that can come up that we'll talk about. So in this case, think opposite operations, how the positive 1.6 gives you a negative 1.6 for a 0 or an x-intercept, and the negative 2 becomes a positive 2 for the x-intercept. So definitely keep that in mind. All right, let's move on. So that was our basic introduction, and all that stuff there was some of the things that you hopefully remembered a little bit of from Algebra 1. But now, let's go into a little bit more detail on the actual forms, because as I said before, there are some different ways to write parabolas. Okay, there are three. There's standard form, factored form, and vertex form. All right, so what's the difference? Look at the expressions. So ax squared plus bx plus c. Notice this one where you have a separate x squared term, a separate x term, and a separate c. No parentheses. That's your biggest giveaway to standard form, is the equation is created without parentheses. Unfortunately, there isn't much to go on as far as what these terms can do. The only thing that you can get easily out of standard form is that c is equal to the y-intercept. The values in a and b don't really do much intuitively in terms of calculations along the parabola. The only thing that you can get from this, and which will be the same across all of these expressions, is what the value of a does in terms of its sign. A positive a means that you get a parabola that opens upward like that. A negative a means that you get a parabola that opens down. And that's going to be true among the other forms as well. So, like for example, factored form, it's got a number out in front here. That is also considered the a value. And so because of that, if there's a negative sign out here, it'll open down as well. And if it's a positive number, it opens up. With factored form, notice there's oftentimes two sets of parentheses. Here, like you have two separate x's that you can then multiply together. So if you have two separate x's that are implied with multiplication, that's generally factored form. The easiest way, again, as I said, to see it is if there's two separate factors that each have just a single power of x, then you know you're in factored form. The other kind of variant of this is if you have an expression like this. Say 3x times x minus 7. This is also considered factored form as well because you have separate x's that are being multiplied together. Notice this one doesn't need the parentheses. This is still factored form because I could write this as 3x minus 0 times x minus 7. Now, writing x minus 0 is kind of pointless, right? Because that's just equal to x, and that's why the x is by itself. So we generally don't write this, and so I'm just going to go ahead and erase this and just let you know that you won't really see that. Instead, you'll see this, and this is also factored form. Okay, vertex form. The vertex form of a quadratic is this. Now, this is a little bit tricky to see here, but the key with vertex form is the fact that you have one set of parentheses where the entire factor is squared. In this particular case here, HK is the vertex. So this expression is useful when you know the vertex of the parabola, and that's what H and K will represent. But be careful here. One big piece here is notice that the H and the K are opposite sign. And so what's happening here is if I need to take an equation and pull the vertex from it, H will flip its sign, much like we did with factored form. Like if you remember before, here, let's go back a page, how we changed signs to pull the x-intercepts. Here, we do the same thing with H. But K does not flip its sign. When it's not in parentheses, there's no need to flip its sign. So you'll see how that happens as we go through a few examples of that. Okay. So expressions in different forms can be used to define even the same function. So let's look at this. So we have a standard form, a factored form, and vertex form. Guys, believe it or not, these are the same parabola, and they refer to the same graph. But notice how the numbers are different. So in this particular case, we want to know, what each of the information could be. So depending on which way the parabola is written, we can easily pick up different pieces of information. And if we happen to have all three like this, we can find all of it super quick. Okay, so which form would you use if you want to find the x-intercepts? Well, the x-intercepts, don't they come from the factors? That means you want to use factored form for this, because they come from the factors. And so what actually are the x-intercepts? So once again, what numbers make this equal to 0? X minus 3 equals 0, x minus 1 equals 0. Looks like 3 and 1. So 3 minus 3 is 0, 1 minus 1 is 0. So these are your x-intercepts. All right, what about the vertex? Well, again, easy from the wording, right? Vertex form is what tells us the vertex. Just be careful because of a sign change and then a lack of one. So when you want to pull the vertex out of this, right? The vertex of this is going to be positive 2, negative 1. Note that the x-coordinate changes sign. And the reason for it has to do with the fact that, once again, I want to know when the factor is equal to 0, because that's when you're going to have that minimum or maximum. That's when you're going to have that graph change direction. And so 2 minus 2 gives you 0. But here, this minus 1 doesn't have to change signs because on the outside, I'm not solving for 0 anymore. What I'm doing is this is actually, to use some words from a later unit, this is going to just shift all our values 1 unit down. So the vertex here will be this. And if you're not sure, then try it out. Take the 2, plug it in for x. This is just going to turn into 0 and vanish, and the negative 1 is going to remain there unchanged. So that's why that one does not change sign. So just be careful. For the y-intercept, well, which one would we use? Well, the reality is either standard or factored form are pretty good for this one. But we're going to say standard because we haven't used it yet. And with standard form, we don't have to do any math. Factored, we have to do a little with the multiply. But standard form, the constant term is 3, so my y-intercept is also equal to 3. And I know that because if I plug 0 in for the other x's, I'm going to get 0 minus 0 plus 3, which is 3. So just be careful, though, with that vertex form. That's important. Okay. Here's one other simple test that you might have done in Algebra 1 as well. Here's an equation in factored form. And I want to put it into standard form. Well, first off, before I do that, let's run through a couple things. There's one thing I want to show you here, and that has to do with x-intercepts. So once again, can you tell me what the x-intercepts are? Always useful to do this. Well, let's find x first, okay? So x-intercepts, x plus 5. So what value do I plug in that makes this equal to 0? Negative 5, right? Again, think opposite sign. Let's do the same thing here. So x equals negative 3, but that's not going to do it, right? Because negative 3 times 2 is 6. Oh. So what happens? Okay. Well, let's erase this. This doesn't look like it's completely right. Instead, I'm going to go over here. I'm going to actually solve this for x. Take the 2x plus 3, set it equal to 0. Add 3 to both sides. So I know I still get that. Oh, wait, 2x plus 3 equals 0. And I'm going to subtract here. Okay. Oops. Kind of got ahead of myself there. So we're going to subtract 3. And you have a negative 3. Okay. So that's where the negative 3 comes from. But this doesn't solve for x. How do you get rid of the 2? You divide it. And so my x-intercept is negative 3 divided by 2. So think opposite operations here. Negative 3 and then divide by 2, which is the opposite of multiply. Oops, scared of that little thing there. Okay. So now that we have that out of the way, I'm going to Now, briefly, I'm just going to do, because I feel like doing a different color here. Um, boop, we'll do purple. There we go. Perfect. Okay, so I want to leave that in black, and I want to change colors to do the rest of this. So one technique that you probably use in Algebra 1 is actually multiplying this out, right? Okay, so let's move some of the stuff here. It's in the video now, so we can erase this. So suppose I wanted to know the y-intercept and not the x-intercept, right? So I'm going to keep it over here. Again, you know what I'm going to do is do up here, x equals -5 and x equals -3/2. I'll keep those there for safekeeping. You may remember that you could try to use a box to multiply, right? So there are two ways to do this. But the biggest way with the box is to just take each of these terms and putting them in a different spot. So on the left side, maybe I'll put x and 5, and then over here, 2x and 3. Keep in mind that if one of these were a negative, that you can make that term negative as well. And now, each box is the result of multiplying its two pieces together. So what is 2x times x? 2x squared. How about 3 times x? How about 2x times 5? And how about 3 times 5? 15. So now, combine my like terms. Remember, x squared is not a like term to x. Are not like terms. Because one's a square and one's more of like a line. So what actually is this? This becomes 2x squared plus 13x, because these I can add together, and then plus 15. The 15 is going to be the y-intercept. So now can you see how, as a shortcut, you can just simply take these two constant terms and multiply them together? 3 times 5 is 15. Also, if I plug 0 in for x, I'm just going to do 5 times 3 anyway. So my y-intercept is 0, 15. Now, do you need the box to do this multiply? No, because a lot of people also know that you can just do x times this, 2x, x times 3, 5 times 2x, and 5 times 3, and you get the same thing. So whether you use the box or not doesn't matter to me. If you like the box because it's a nice visual, go for it. But if you think, no, I can do the multiply, then that's perfectly fine too. So knowing factored form first certainly helps get you to standard form. So now here's my question. Is it possible to go the other direction? Can I take standard form and go backwards into factored form? Yes, you can. More on that in a few lessons. We call that factoring. Okay. So real quick here, let's match each quadratic expression in factored form with its equivalent expression in standard form, right? All right. So one thing that we can do is we can kind of do, maybe we'll do one of these or two of these together, and let's see what comes up with. First thing to note, though, notice this 32 and some of the numbers on here. Remember that these are your y-intercepts. The only way to get these numbers is to actually multiply these last constants together. So 2 times 6 is 12. So that one's either going to match 2 or 4, because 2 times 6 is the only way you're going to get that 12. 8 and 2, well, 8 times 2 is 16, right? So that's got to match there. 8 times 4 is 32. Oh, wait, we got a 32. So now this one also must be 2 and 4. So you can pick one, and you can multiply it if you'd like. So maybe we'll do the first one. If I do x plus 2 times x plus 6, I get x squared, 6x, 2x, 12, which is x squared. These are like terms. Sorry for my messy handwriting. 8x plus 12. So it looks like this one matches number 4, and then D matches, number 2. An easy way to also see that is x times 2x is 2x squared. And then this one is the other one that has a 12. So it's got 6 times 2 is 12, and x times 2x being 2x squared. Has both of those. So here I showed you one quick example, but with a little bit of logic, we didn't actually have to multiply all of them out, which is kind of nice. All right. How about this one? Select all expressions that are equivalent to x squared plus 4x. Well, so what's going to happen? That means we're going to have to do some multiplying again, right? So you can try using the box, or you can simply multiply each term. So when the x is attached to parentheses, we have to multiply by each term in the parentheses. So you get x squared, x times x, and x squared, x times 4 is 4x. It matches. That one works. How about this one? You get x plus 2. Now, if it's squared, right, be careful. Do not distribute the power. That's a big no-no. Powers do not distribute across addition and subtraction. They do across multiplication and division, but not across this. The only way to do this is to write 2 copies of it. X plus 2 times x plus 2. And then you can multiply. Again, you can use the box if you'd like by doing x and 2 and x and 2. X squared, 2x, 2x, and 2 times 2 is 4. And so this equals x squared plus 4x plus 4. It's got that extra 4. Not B. What about C? Well, let's try it out. You get x times x is x squared. X times 4 is 4x. X times x is another x squared. Another 4x. And if I combine my like terms, I get 2x squared plus 8x. Keep in mind when you add powers, add terms together. When all the like exponents get added, it does not change the exponents. X plus x does not go to x squared. X squared plus x squared does not go to x to the 4th. But be aware that you should probably have room to count some of these, as you combine like terms. Okay, anyway, what about so we know this one is not it. What about E? Let's jump to E for a second. E is the same as A, right? You can multiply, but whether you distribute this way or front ways, doesn't matter. E works. What about D? Well, x plus 2 squared is the same thing as this, right? Okay, same expression. So it's x squared plus 4x plus 4, but there's this extra minus 4 on the end of it. What's 4 minus 4? 0 goes away. X squared plus 4x, and that one also works. Notice D is in vertex form. This is standard form. This one is in factored form. And then this one is in vertex form. Food for thought. Okay. Oops, I sketched that by accident. All right, next page. All right, looks like we're approaching the end here because I don't want to make this video too terribly long. But let's answer these questions as much as we can. So the function f is given by this, right? X minus 2 times x plus 4. So again, it is in factored form. All right, what are the x-intercepts of the graph? And we're going to do this without technology. Okay, again, what makes these equal to 0? Looks like it's going to be a 2 here. So, oops, let me erase this mark here. So we are going to have positive 2 and negative 4. Let's actually plot them on the graph. So they're going to be 2, 0 and negative 4, 0 because the y-coordinate we're saying is 0. We want to know what values produce this output of 0. So 2, 0 and negative 4, 0. What are the x and y coordinates of the graph? Ooh, okay. So it's great if we have vertex form. We don't. Can we write it in vertex form? Yeah, but that requires completing the square, and we're not there yet. Yeah, that doesn't even sound very good, does it? Anyway, what else do you know? It says, how can we use the x-intercepts? Hey, wait a minute. Isn't a parabola symmetrical? And that means this parabola is going to have to go through these points in a way that these are balanced out symmetrical. So how does that work? The line of symmetry would have to go halfway in between them. Because the left side and the right side of a parabola are always mirror images of one another. So how does that help us with the vertex? Well, we know that the vertex is on this line of symmetry. The vertex is where the line of symmetry crosses the parabola itself. So what do we know about this dotted line? So the dotted line is located at an x-coordinate of negative 1. That's your axis of symmetry. So the vertex is going to be negative 1, comma, something. Okay, so what's that something? We're going to take the negative 1 and we're going to plug it into the function. Because we want to know where is that on the parabola. So we're going to do, negative 1 minus 2 times negative 1 plus 4. We're going to plug in for x. And that's going to get us negative 3 times negative 1 plus 4 is positive 3. And that's equal to negative 9. So my vertex is at negative 1, comma 9. 1, 2, 3, 4, 5, 6, 7, 8. Whoops. Oh, we're like way down here. Whoopsie. A little off the graph. That's okay. All right. And so now we know, so great, is that the y-intercept? No. Remember, y-intercept occurs then x is 0. So plug 0 into this function. So let's write here, -1, -9. So going over here, we're going to plug 0 into this function, and then we're going to get 0 minus 2 times 0 plus 4, or just multiply the two factor numbers together. And you get -2 times 4, -8. There's your y-intercept. Notice it's a different point than the vertex. Now sketch a graph that represents this function. Okay, kind of hard to do, but here's one thing. Remember, parabola is symmetrical, so if you have a point just on the right of the line of symmetry, it will also have a matching point on the left side. And then all you got to do, oh, not bad. Did that pretty well, actually. Could be a little worse for wear, but hey, that's totally fine. It would have to pass through all of those points. And that's how you sketch a parabola based on information. So here, find x-intercepts first. Finding the y, finding the vertex can be done in any order. Actually, any of these could really be done in any order. Although the intercepts are probably the easiest find first because it's in factored form. Okay? If I gave you a different form, say standard form or vertex form, I would put these questions in a different order. So for example, if I had standard form, I would do y-intercept first. And then from there, I could figure out, maybe convert it to another form to do the rest. If it was in vertex form, I would have started with number 2. And I would have gone from probably 2, from that point probably to 3 and then back to 1 again. But, it's hard to tell that. Okay. So, we're almost done, folks, here, I think. One more thing I want to really kind of hammer out here is, again, vertex form. It's very important to kind of know the difference between the different orientations when you're dealing with vertex form. So let's take a look. Remember our original form. So our original form is y equals a, x minus h squared plus k. Keep in mind the h changes its sign when you find the vertex. K does not. That's kind of the purpose of the negative sign. So if we have this equation, x plus 10 squared, what is the value of h and what is the value of k? That's what I want to know. What's h and what's k? So notice how the equation has a plus 10 in it, but we'd expect a minus sign. So my vertex is -10. Now, what number is after the factor? Because here we're supposed to have a plus k. Do I see a number here? If I don't have a number there, and it's supposed to be plus something, well, what can I put there that doesn't change this equation? I could put a plus 0. If there's no number after the parentheses, put a plus 0 so that you know that the vertex will be a 0. Now question, will the graph open up or down? The difference lies in the A, which essentially is telling us, does it start with a negative? If it does, it goes down. If there's no sign there in front of the parentheses, opens up, like this one. That one opens up, starts with a positive. Same thing here, starts with a positive. Now what's the vertex in this one? Change sign, don't change sign. +4, positive 8. All right. Next one, same equation, right? But the only difference is the inclusion of the negative sign. Guess what? This one will still be 4 comma 8. Those rules do not change even when there's a negative out here. So those rules are constant. All that the negative does is it takes the parabola and flips it. I said positive there. Down. So this parabola opens down. Okay. What about this equation? This doesn't look like vertex form. Ah, but it actually is. Question, what's missing from this? It's missing that set of parentheses, right? The x is there, but the h is not. So a number being added or subtracted to x isn't there. So again, if this h isn't there, what value can you use? 0. And what is the value of k? So, don't change the sign. -7. All right. Normally I wouldn't record a yawn like that, guys, but I'm almost an hour into this video, so I am not recording that over again. Just so that you know. All right. Coordinates of the vertex is here. So the vertex is actually sitting on the y-axis with this equation. Is it going to open up or down? Up. Again, starts positive. What about here? Do fractions matter? Not at all. And actually, in this unit, fractions are going to be your friend. So it turns out this will open up. What's the vertex? -3, -5. Again, change the sign, doesn't change sign. How about this one? Vertex, -100, 50. No sign change, no sign change. Open up or down? Down. So both of them will have that vertex at -150, but if I were to remove the negative sign, it just literally takes the parabola and flips it almost 100, like basically flips it 180 degrees. What about this one? What's the vertex here? Oh, it's all letters. Remember, who cares if it's letters, right? Still the same idea exists. Sign change, -m. No sign change, +n. Now, does the graph open up or down? Depends. If A is positive, it opens up, and if A is negative, it opens down. That's the key. So, if A is greater than 0, up. A is less than 0, down. But if A equals 0, what happens? You now have a line. It's no longer a parabola anymore. So you won't see that condition here. All right. So very important to remember kind of how to grab the vertex out of vertex form and whether or not a function opens up or down. All right, folks, we made it. And, looks like we are just approaching the 1 hour mark on this video. Sorry that was a long one, but there's a lot of information to get through. Hopefully the other videos won't be nearly as long as this one. We'll try to break it down. So feel free to scroll through this for as much as you want. And go back, review your material. This video will always be there for you to review and practice as need be. So work in your colored packets, and there you go. So I hope you have a lovely evening, folks. Take care, and I will see you in class. And I'm going to pad the last 5 seconds to make this equal an hour. And all right, take care, folks.